Hi, this is Sung. I'm the principal and director of Sky Academy, and in this particular episode, what I want to do is continue the work that we've been doing on functions and relations. And of course, we've been looking at the whole idea of relationships or relations being any sort of set of first terms that are related to a second term, okay? Any ordered pair relationship, okay? And we kind of looked at how functions are special to that, because there are many to one relationship. Remember that whole idea? Well, and then we looked at the whole idea of domain and range, which looked at the horizontal bandwidth of a function as opposed to the vertical bandwidth of a function being the range. Okay, so domain and range. Now what I want to do is look at this whole idea of odd and even functions. Now, let me just say at the outset, most functions will neither be odd nor even. In fact, a lot of them will be neither, all right? But you might on the occasion, right, I was gonna say on the odd occasion, you might on occasion find that that relationships are, or functions are, either odd or even. So let me just demonstrate, or let me just explain what odd functions are. Let me explain what even functions are. So if you've got a relationship or a function that's governed by the rule y is equal to f of x, then if you have the rule obeying this particular property, which is what f of minus a equals to the minus of f of a, then you've actually got what we call an odd function, all right? So algebraically speaking, if you substitute in as the first term a negative of a, then that will give you a result that's equal to the negative of the positive of a, okay? And vice versa, yep. So basically, the algebraic test is that, all right? The way that will pan out geometrically is that an odd function will have rotational symmetry about the origin, which basically means this. If you turn this function, or if you turn the number plane that this function sits on upside down and rotate it at 180 degrees, you would have exactly the same function, okay? So if you did that and you turned it upside down, it would sit on top of itself, okay? And an example of an odd function would be y is equal to x cubed. And I think part of the reason why it's called an odd function, in fact, I'm pretty sure this is why it's called an odd function, is because when you've got y is equal to x to the power of an odd number, it will give you an odd function. Let me demonstrate by using the algebraic test, all right? So if you've got, for example, x equals to a, f of minus a would be equal to minus a to the power of 3, which ends up equaling minus a cubed. Does that make sense? Now, f of a would be equal to a cubed minus f of a would be equal to minus a cubed. And can you see that minus f of a is going to be equal to f of minus a? Do you see that because these two are equal, these two are also equal? Do you see that? So algebraically speaking, this function is an odd function. Yes? Now, geometrically speaking, if we were to graph this, right, this particular function is a cubic function that will look like this. Does that make sense? Yep. And if we turn this upside down, can you see that if you turn this upside down, it would pretty much map onto itself? Do you see that? That's what makes this odd, okay? Not odd as in strange odd, but odd as in this particular property of odd functions, yes? So basically, the algebraic test is f of minus a equals to minus f of a. When it comes to even functions, all right, and let me just underline the heading here. When it comes to even functions, what you're actually doing is the algebraic test would be f of minus a is equal to f of a, right? And this will be true of functions where y is equal to x to the power of an even number, okay? So let's have a look at that. So when x is equal to a, f of a equals to a squared. Do you see that? Now, f of minus a would be equal to minus a all squared, which is a squared, which is also equal to that. Do you see that? Okay, so we can say, and safely say, that y is equal to x squared is an even function. Okay, good. Now let me show you what an even function will look like. Let me come around this way. An even function will have line symmetry about the y-axis. So in other words, it will pretty much map onto itself. So in other words, if we were to spin it like this, spin it like a doner kebab, right? Then basically the right-hand side of the graph will map onto the left-hand side of the graph. Do you see that? So, and obviously that's the case with this. Y equals to x squared is a quadratic or a parabola, all right? And it will do exactly that. It will map onto itself. Yes? Good. Okay. So let me just also say a couple of other things. Just say we were to move or shift this graph to the right or to the left, right? Would it still have an axis of symmetry? And the answer is yes, it would still have an axis of symmetry. But would the axis of symmetry be the y-axis? So if we shift this graph to the left, the y-axis would no longer be the axis of symmetry. Do you see that? If that's the case, this graph shifted to the right or to the left will no longer be an even function, right? It'll be a symmetrical function, but not even in nature. And also with an odd function, if we were to shift it up or down or to the left or to the right, if we were to rotate it about the origin, it would no longer have rotational symmetry about the origin. It's no longer even. It's no longer odd, even though it has rotational symmetry at some other point. Okay, so for it to be an odd function, it needs to have rotational symmetry about the origin. For it to be an even function, it needs to have line symmetry about the y-axis, and it's very strict when it comes to that. So that is why I say, as I said before, most functions will be neither odd or even, and it's on the rare occasion that you will find a function being one or the other. Okay, thank you very much for watching. In the next episode, we'll be continuing on with functions and relations. Yep. And I look forward to seeing you in the next episode. Bye.